Hello, my name is Luke Barnes, and I'm a fourth-year mechanical engineering student here at the Georgia Institute of Technology. In this video, I'll be discussing 5 fascinating topics in modern manufacturing and industrial processes. This video serves as a submission for Project 3 in Dr. Hassan Rashidi's ME 3210 class, Design, Manufacturing, and Materials. The first topic I'll be discussing is CNC machining, which stands for Computer Numerical Control Machining. While there are many technologies that are based on the principles of computer numerical control, the most common use of the term applies to a type of automated milling machines. CNC mills are a type of subtractive manufacturing where a spinning cutting tool follows a precise, pre-programmed path to remove unwanted material until all that remains is the final part geometry. CNC mills receive their instructions by parsing consecutive lines of geometric code, or G-code, each of which includes some type of movement command as well as the positional coordinates denoting the start, end, or other parameters of the move. Examples of these commands are rapid traverse, linear, and arc movements, as well as dozens of G-codes commanding the controller to turn on and off the coolant, select spindle speed, change modes of operation, and many other commands. By executing thousands of lines of G-code commands in sequence, complex geometry can be repeatedly machined out of a wide variety of machinable materials, including most types of metal, many plastics, composites, and even wood. CNC machining is the backbone of many manufacturing industries. The versatility and precision of these machines is unparalleled, making them well suited for a variety of precision or low-quantity parts. As a primary means of manufacturing, CNCs are used to create aerospace hardware, biomedical components, custom automotive parts, and many other precision hardware. Even products that are produced via injection molding, die casting, stamping, and many other low-mix, high-volume methods often depend on CNC machines to produce the molds, jigs, dies, fixtures, and other tooling unique to each part produced. Machines are capable of producing a wide variety of part geometries. They are not well suited to all applications. The primary limitations of CNC machining include excessive chip production and material waste, weaker surface properties, higher cycle time per unit, and complex fixturing requirements. However, their ability to produce a broad range of parts with limited custom tooling make them indispensable in manufacturing industries. The next topic to be discussed is sheet metal forming, where CNC machining excels in its versatility in creating parts with a relatively low ratio of surface area to volume. Sheet metal forming is capable of producing parts with a relatively thin and relatively uniform thickness. For many use cases, this results in a much greater material efficiency. Parts produced by sheet metal forming are unable to meet the same standards of precision as high-end CNC machines, but the parts produced are often lighter, cheaper, and more compliant. Some types of sheet metal forming are shearing, bending, stretch forming, deep drawing, and punching. Common products manufactured using sheet metal forming techniques are aircraft fuselages, car chassis, roofing, brackets, soda cans, and HVAC ductwork. Metal forming is one of the oldest metalworking techniques, with early forms of hammering and stamping originating over 7,000 years ago, and possibly even earlier than that. However, that does not mean sheet metal forming techniques have stopped evolving. To combat the high cost of custom tooling associated with many sheet metal forming processes and inherent limitations with current techniques, companies like Machina Labs hope to redefine the future of sheet metal manufacturing capabilities. By building AI-defined and robot-executed generalized sheet metal forming workflows, Machina Labs hopes to extend cost-efficient, low-volume or high-precision capabilities to a reimagined future manufacturing ecosystem. Whether it's the basic forming techniques that have been around for millennia or the ultra-modern AI-driven robotic cells of the present, sheet metal forming has long been and will continue to be one of the most important manufacturing techniques in industry. CNC machining and sheet metal forming demonstrate how advanced manufacturing techniques allow us to create complex, high-precision components, whether it's cutting a metal block into an intricate shape or forming a metal sheet into a durable, lightweight part. However, achieving such precision in manufacturing relies heavily on the ability to measure these parts accurately. This is where metrology comes into play. Metrology, the science of measurement, ensures that manufactured components meet exact specifications and quality standards. Whether machining a custom automotive part or forming a lightweight aerospace component, Precise measurement is essential to validate that the part meets design intent and functions as required. However, one of the limitations of metrology is the amount of time it requires to inspect each unit. As a result, most manufacturers rely on sampling techniques to deliver high-quality parts confidently without fully inspecting each unit. There are a wide variety of metrology instruments used to verify the dimensions and tolerances defined by GD&T, or geometric dimensioning and tolerancing, on a part's engineering print. These instruments include pin gauges, thread gauges, calipers, micrometers, coordinate measuring machines, otherwise known as CMMs, optical comparators, and many others. Pin gauges and thread gauges are used to verify the diameter, roundness, and depth of holes, while calipers and micrometers can be used to measure the dimension between two features on a part. Optical comparators excel at inspecting surface quality and dimensional accuracy. Finally, CMMs are the most generic instrument on this list, analogous to a CNC for inspection. CMMs measure predefined points, features, and surfaces by probing and measuring mechanical contact. Traditional manufacturing plants often consist of distinct design, production, inspection, and testing departments, each handling different stages of the manufacturing process. CNC machining, sheet metal forming, and metrology, along with assembly, materials handling, shipping, and countless other factory stations, are examples of some of the interconnected processes in many manufacturing plants. While this structure allows for specialized expertise, it also introduces inefficiencies and waste due to miscommunication and delays between workers, machines, inventory, and quality teams. This is where the Industrial Internet of Things, or IIoT, comes into play. By connecting equipment, sensors, and inventory systems across these departments, IIoT enables real-time data sharing and seamless communication between all parts of the manufacturing process. With IIoT, a machine can automatically report its maintenance needs or production status, and metrology equipment can feed quality data directly to production managers, reducing downtime and wasted production in the event of emergent nonconformances. The primary benefits of an industrial Internet of Things is its ability to collect massive amounts of structured data about the status of a manufacturing plant across years of operation. This can lead to valuable operational insights, saving companies huge amounts of money and time in the long run. However, IIoT is not without its risks. Networks of interconnected machines can leave plants open to greater risks of cyber attacks, as well as the added cost of managing and processing the immense amount of data produced. Furthermore, recent events such as the CrowdStrike incident have highlighted the risks of over-dependence on modern computer systems. However, in many cases, the benefits of this Industry 4.0 approach to manufacturing greatly outweighs the risks. IIoT can provide the infrastructure for better data collection and signaling between parts of a production system. Technology alone isn't enough to ensure an optimal production environment. This brings us to Lean and Six Sigma, methodologies designed to enhance manufacturing efficiency and quality. By focusing on reducing waste, optimizing process flow, and ensuring consistent quality, Lean and Six Sigma principles complement the technological backbone of advanced manufacturing. Together, they provide a structured approach to problem solving and continuous improvement, allowing manufacturers to achieve high levels of accuracy, reduce costs, and improve customer satisfaction. One of the primary methodologies included in Lean Six Sigma Toolbox is DMAIC, which stands for Define, Measure, Analyze, Improve, and Control. These 5 steps guide managers and process engineers through a targeted cycle of continuous improvement. Six Sigma methodologies are especially crucial in environments where high precision, reliability, and minimal waste are essential, making them ideal companions to the processes and systems we've already discussed. There are very few cases where Lean Six Sigma wouldn't help improve a process, but it's important to be aware of the challenges in implementing these methodologies. Primarily, Lean Six Sigma requires that all stakeholders are brought into the mindset of continuous improvement. Additionally, it can take a significant amount of time and resources before the results of this approach will be visible in the bottom line of the company. In conclusion, Lean and Six Sigma provide a toolbox of management and operational methodologies to direct complex interconnected industrial systems. In the manufacturing context, CNC machining, sheet metal forming, and other fabrication techniques underpin the production of both novel and extremely high-volume goods. Metrology provides a language and a set of standards for verifying the conformance of the units produced. Finally, the Industrial Internet of Things paves the way into a future of flexible, efficient, and highly automated factories. Disclaimer: this video is intended for educational purposes only. The content in this video is not intended to be used as business or manufacturing advice. Thanks for watching. I hope you enjoyed the video and learned something new about these manufacturing topics. The following sources were used in the production of this video: